In our previous notes and discussions, we've looked at how to analyze circuits through the method of reduction by equivalent elements, by lumping things together into parallel or series combinations. It turns out that there are plenty of circuit networks out there that you can't reduce by that method. And so what we want to discuss in this set of notes is what you do in the general case. So we'll be looking at what's known as a general Kirchhoff's analysis. There is a way to deal with such circuits, but you have to follow this somewhat more complicated, more general approach. To introduce the idea, I'm going to consider a particular circuit where I've got two different batteries now, each with their own EMF. I've got E1 here and E2 here. And I'm going to wire both of these batteries with their positive terminals, the ones with the little nubs, connected to the top of some resistor. These are ideal wires then connected to some actual conducting material that offers some resistance R. Now I've begun the lecture here with a three-dimensional diagram because I want to begin by making a point about how actual batteries work, how they function. It turns out, as you recall, when we discussed the inner workings of a battery, if we focus just on E1 for the moment, that in those cases, there's some chemical reaction which occurs inside the battery, and that then as the reaction releases its energy, it ends up bringing positive charges to the top terminal of the battery, leaving negative charges on the bottom terminal, and that chemical reaction will occur until the energy it releases matches the amount of work required to bring up the positive charges from the bottom of the battery up to the top of the battery. That's how we know that the batteries maintain this magical constant potential difference from their bottom to their top. However, if we then take such a battery, a real battery, and wire it into a circuit like this, where now current becomes to come off of the top of the battery, things begin to change. That chemical reaction can only occur at a certain rate. And if these currents get large, we'll be removing positive charges so quickly off the top of the battery, we won't be able to replace them sufficiently quickly. There will be a drop in the total charge on the top plate of the battery and a corresponding then drop in the potential of the battery when there is a large current. The empirical observation is that actually that drop off in potential across the battery to a good approximation for reasonably sized currents is actually a linear drop in potential. So the way we can model that, the way this is often modeled and which reflects this approximate linear drop off in potential across the battery with current is as follows. What I'll do is I'll represent this battery, this realistic battery then, as some kind of a lumped circuit element, and what I will use to represent it then will be an ideal EMF, which is what these symbols here always indicate with the two parallel lines. But that ideal EMF then is going to be in series with a little resistance representing what's going on inside of the battery. So it is actually this unit here inside the dash box that represents the first battery, where we still have the ideal EMF E1, which gives us the voltage across the battery if there were no current flowing. And then this linear drop-off in potential that we lose, we can represent as a model, a resistance, an internal resistance this is called. And for that, I will use a lowercase r with a subscript of 1. Okay, so that represents the first of my batteries. The second battery on the other side, I will represent in exactly the same way with some internal resistance, R2. My ideal battery symbol with its plus and minus plates. And then that continues down until I get to the edge of this lumped circuit element. This, of course, has EMF E2. And then finally, of course, my resistor here, I can simply represent then as a standard resistor symbol. Will look like so, with its resistance R. That's its actual resistance. And then finally, I can complete my circuit with the corresponding ideal wires that connect the top of these two batteries to the top of the resistor, and the bottom of those batteries then down to the bottom of the resistor. Now, That then is the circuit that we intend to analyze today. Now, you'll notice that although I have a number of resistors here, I can't lump them together as any kind of series or parallel combination. It just is not amenable to that kind of reduction. If you look at first, you might think, well, wait a minute, R1, little r1 and big R certainly appear to be in series with one another, but there's this interesting junction up here that connects things to R2. And in fact, if you remember our definition of a series combination of circuit elements that our whole derivation depended on, there were two things. You needed the voltage through the series to be the sum of the individual voltages. It looks like that might work, because to get the potential from here to here, the voltage, I would just add this voltage to this voltage. The difficulty, though, is that in a series combination, you also need the current to be identical through these two resistors. But the current that comes through R1, some of that current actually, all that current might go through the resistor R, but there's additional current coming in. So the current in these two elements will not line up. So these two you can't think of as in series. You also might think of R1 and R2 perhaps as running in parallel to one another. The parallel combination, as you know, needs to have the sum of the currents, to the total current going through the system to be the sum of the two currents. And certainly I can imagine that if I have current I1 from battery 1 across the top here and current I2 from battery 2 across the top over here, that the total current flowing through these two internal resistances is the sum of those currents. But now notice the second part of parallel combination, that the voltage across the two resistors have to be identical. That will not necessarily follow, because these resistors are in fact connected to batteries of different voltages before they are connected together. So this is just a much more complicated situation. Nonetheless, we can analyze it using Kirchhoff's laws. Now, if you start to think about applying Kirchhoff's two laws, as you know, what we would do is we would look at the junction rule. And there's a whole series of various different junctions here that we could begin to analyze. Particularly this junction here looks very important, as well as this junction down there. There are other junctions, between the resistors and the batteries. So we could write down a large number of equations for those junctions. Moreover, when we come to the loop rule, there's a whole series of loops, in fact, that I could begin to analyze. I could analyze this loop around this part of the circuit, or I could analyze a loop around this part of the circuit, or I could write another equation that loops around the entire circuit, or I can write a loop that kind of goes around in some kind of a crazy figure eight. I've got all kinds of options. I can end up writing down many equations and then end up with a very difficult mathematical problem to solve. So over the years, I've developed an approach which is guaranteed to keep your work as simple as possible. What this approach will do is actually limit the number of unknowns that you have to deal with, and also limit the number of equations to exactly the minimal number of equations, so that you can solve for the circuit behavior much more easily. So my approach goes in two steps. The first part of my approach to deal with Kirchhoff's first law, the junction laws, is that I'm going to use this law, okay? So we're going to use the law to introduce, so I'm going to start to introduce some unknowns, the unknown currents, but the key is that it's going to be the minimal number of unknown currents. Now, so let me try to illustrate here exactly what I mean by this. So, for instance, in this particular problem, I'm asked to solve for the current I1 coming out of this battery. So if I go and I look at my circuit, by using Kirchhoff's laws, right, the first law, I know that if the current flowing out the top of this resistor R1 is I1, that I must similarly have that same amount of current I1. It actually must be flowing up into the resistor from down below. That must actually match the current flowing across the battery. it must, by applying the junction rule to this point here, equal the amount of current flowing, this was I1, flowing along this branch coming down below, so that current I1 flowing into this junction matches current I1, which is what must be flowing up through this battery. So far, with just this defining this one unknown I1, I'm able to specify all of the currents around this section of the circuit. Where I begin to run into trouble, though, as you can see, is when I want to figure out how much current is flowing down through this branch, how much current flows actually through this resistor. I can't write that solely in terms of I1 because there's additional current that could be coming in through this branch. So at that point, I actually have a choice. I could introduce an unknown that represents the current flowing through this resistor, right? And then use that and my knowledge of I1 to determine how much current is flowing through this branch of the circuit. Or what I could do, and this is what we will do, because we're actually being asked for these two currents, I1 and I2, what I can do is define now my next new current, I2. Once I decide to call the current flowing through this branch I2, then I know automatically, through Kirchhoff's law, that what is flowing through this junction must be the total of those two. It must be equal to I1 plus I2. And similarly then, that is how much current is actually flowing down through this resistor until I get to the junction point down here. Once I'm at this junction point, I have I1 plus I2 coming down. I know I1 peels off this way, so I know therefore it must be I2 flowing over to the right. And then following these junctions along, there's no other branches coming in. I know that I2 is what's going to flow up through my battery. There's going to be I2 then flowing up through my resistor R2 back around the circuit. So I've now been able to label the currents flowing through all of my branches solely in terms of the minimal number of unknowns. I only introduced an unknown when I needed it, and I kept using the things I had defined previously to make sure I introduced no extra unknowns. Next, then, having exhausted all that we can get out of K1, now it's time to try to solve for these two unknown currents, and we therefore will need to generate some equations to solve for them. That's where we begin to use the voltage law. So to apply K2, what I'm going to do is I'm going to write, okay, now to keep the equations down to a minimum, the strategy is I'm going to write one equation for, and now if we think about it, there are many possible loops that we could employ, as we had pointed out previously. But it turns out that if you're very careful and you just write one equation for each, what I will call an innermost loop, for each innermost loop, and then we can simply solve. But the key is to look for these innermost loops. Now, the loop I had referenced that goes around the outside of the circuit, that's certainly not an inner loop. This guy here, though, notice he's an innermost loop, right? There's no like sub-loop associated with him. He's sort of a primitive loop in the system. In a more complicated circuit, there may be a number of these innermost loops. In our case, there are simply two of them. So let me just kind of indicate these two loops for us here. I know the diagram here is getting a little bit busy, but let's see if we can sketch those in there for you here. I'll try to draw it kind of lightly. So here is one loop, right? That loop I will call L1. And here is a second loop that goes around this branch of the circuit in a direction kind of like this. I will call that loop L2. So our job now is to go around each of these loops and to write down the corresponding loop equation to provide a system of equations that we then would be able to solve. So let's go forward then and try to carry out that exercise. I'll start with loop 1. So let's just slide our page up here just a little bit so I can keep my diagram in view. and I'm going to now write down the loop 1 equation. So for loop 1, if I take a careful look here, I want to go all the way around this loop, and to do that, and to get my sign straight, remember, we always want to mark the upstream and downstream side of our resistors. The presumed direction of I1 is this way, so the upstream side of R1 is here, plus, and the downstream side is minus. For this resistor, right, I've written the current as though it were flowing in the downward direction, so the upstream side there is plus, and the downstream side there is minus. And similarly, as long as I'm at it here, if we look at R2, the current is flowing upwards through here. That's the sign convention we chose for that current. So this will be the upstream side of resistor R2. That will be the downstream side. Okay, now with those labeled, we're ready to do our loop equations. As usual, I always like to mark my starting point here with an X so that I don't go too far around my loop, right? And that I actually do go all the way that I need to go around my loop. So let's now write this particular loop equation. So the loop equations always say 0 equals the sum of the potential changes, or the voltages, as I go around my loop. In this case, as I go around the loop, the first thing I do is I go up through battery E1, up through this EMF, from the minus to the plus side. So that's always going to be a positive potential. So it's going to be plus or minus, but it's going to be the plus choice because I'm going from the minus to the plus on that battery. EMF E1. Next, I come across this resistor R1. The change in potential will be either plus or minus I1 times lowercase r1. In this case, notice I'm going from the upstream side, the plus side of that resistor, to the downstream side, the minus side. Going from plus to minus, that will be a negative voltage because it's a decrease, so I will choose the lower sign in that case. We then come around here, and our loop then goes through resistor R, but we have to be careful now. The current flowing through there is actually I1 plus I2. So it's going to be plus or minus I1 plus I2, and all of that is multiplying that resistor R. To get the sign right, notice I'm going from the plus side of this resistor down to the minus side, so that will be a minus choice. I then have nothing left but wires. Ideal wires, as we've pointed out, always have zero resistance, so their IR term always just gives me 0, so I don't need to account for those, and this then represents my entire loop 1 equation. I can, of course, write this out a little bit more neatly, and we'll do that later on. Let's just get the two loops down here before I scroll up the page. So for loop 2, very similarly, I will start at 0. I'll pick an analogous starting point X. Now loop 2, I have myself going this way around the loop, so let's always be sure to follow our conventions so we don't mess up any signs. Starting here, as I go around, it's all wire, wire, wire. I come to my resistor. The current flowing through it is I1 plus I2. The resistance is R, so that's going to be plus or minus I1 plus I2 times the resistance R. In this case, though, notice I'm going at the direction of my loop, L2, I'm going up through that resistor against the flow of the current. That's going to be a positive voltage. You can also see that because I'm going from a minus to a plus. That would be a gain. So this will be a positive term in this case. Once I've gone through my resistor, it's more wire, 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 wire. Now I'm coming down through this internal resistance, R2. Again, I'm going upstream. I'm going from the minus side to the plus side. So in principle, it can be plus or minus, and the term is I2 times, now it's the internal resistance R2, but because we're going from minus to plus, that would be a gain, so that counts as a plus. Finally, I go through my battery. That's going to be a plus or minus EMF2. And in this case, notice I'm going from the plus terminal to the minus terminal. That would be a loss, right? So we count that as a minus voltage. If this is my reference lead and I put the final lead at a lower potential, the one marked minus, it's going to end up reading a negative voltage on my voltmeter. Okay, so those then here are our two equations. We can then write them down a little bit more neatly. If I tidy this up, the first equation, I'll call that L1, will give me 0 equals E1 minus, is what I had here, plus E1 minus I1 R1. And then it's another minus sign here, minus I1 plus I2R. The second loop equation, L2, then will give me 0 equals, in this case, it's a plus. So I have I1 plus I2 times R. And then I have another plus sign, plus I2 internal resistance R2. And then finally minus E2. And then the final step would be to solve these two equations. To save time, I'm not going to solve these two equations in two unknowns with you right here. You can try this one out as an exercise if you like. It's very good practice. I'll just make some comments on, how to solve such equations. There are a variety of different approaches that you can use. I'm sure you guys are familiar with solving two equations in two unknowns. In this case, since I'm trying to find I1, right, the way I might do this is I might use equation, you pick either one of them, maybe L2, right, to solve for I2, right? And then once I have I2, I would then substitute your result for I2, whatever you get from that first solve, substitute that into loop 1 equation. That will then eliminate I2, and I'll be just left with an equation in terms of I1, and then finally you would solve for I1. That's not the most elegant way, but that's one way that would definitely get the job done. Okay, so that's a general Kirchhoff's analysis. Following those basic rules, the approach that I've outlined for you, you will find that for practically any circuit problem, you can reduce it to a very limited number of equations to solve to determine the behavior of even an irreducible circuit, a circuit that you can't analyze by parallel and series combinations.